What if every choice you've ever made split reality into infinite parallel worlds? Picture this somewhere out there. A version of you took that job offer, missed that flight, or even said yes instead of no. It might sound like the plot of a sci-fi blockbuster, but the idea of branching timelines isn't just Hollywood fantasy. It's a real possibility rooted in the bizarre laws of quantum physics. From Schrödinger's famous cat, both alive and dead in its box, to the mind-bending many worlds interpretation, scientists have spent decades wrestling with the idea that our universe might be just one thread in an unimaginably vast cosmic tapestry. Now here's where it gets even stranger. What if time itself isn't a straight line but a swirling, tangled web of possibilities? Imagine reality as a book where every page contains a different version of history, and each decision you make flips you to a new chapter. Some theories suggest these alternate timelines aren't just theoretical. They could be bleeding into our world, leaving faint echoes in quantum experiments or even in the unexplainable déjà vu moments we've all felt. Could there be universes where dinosaurs never went extinct, where Atlantis thrived, or where you became someone entirely different? The answer might lie in the quantum realm, where the rules we take for granted no longer apply. Today, we're diving deep into 30 of the most astonishing theories about quantum timelines, ideas that will stretch your understanding of reality to its limits. We'll explore how black holes might be gateways to alternate histories, why some physicists believe consciousness itself could shape the multiverse, and whether we might one day find hard evidence of these shadow dimensions. By the end of this journey, you'll never look at a simple choice or the fabric of existence the same way again. So buckle up. Reality is about to get a lot bigger, weirder, and more thrilling than you ever imagined. One of the most mind-bending ideas in quantum physics is Hugh Everett's many worlds interpretation, which suggests that every possible outcome of a quantum event actually happens just in different universes. Think of reality as an endlessly branching tree. Each time a particle could go left or right, or you make a choice, even something as small as hitting snooze on your alarm, the universe splits. In one world, you wake up early and catch your train. In another, you oversleep and miss it entirely, and neither version of you would ever know the other exists. This idea grew out of the famous Schrödinger's cat paradox, where a cat in a box is both alive and dead until someone observes it. Everett took it further. What if both outcomes are real, just in separate timelines? The moment you open the box, reality fractures. One universe holds a relieved, purring cat. The other, well, let's not go there, but here's the real kicker. This isn't just about cats or tiny particles. If the many worlds interpretation is correct, there are infinite versions of you out there. Some might be living nearly identical lives, just with one tiny difference. Others could be unrecognizable. Maybe a version of you became an astronaut or never existed at all. And somewhere in that sea of possibilities, there's a universe where dinosaurs still roam, where history's greatest tragedies never happened, or where you made that one life-changing decision you always wondered about. The implications are staggering. It means every regret, every near miss, every what if isn't just a thought experiment, it's a real, tangible world out there. Some physicists even argue these parallel realities could explain quantum weirdness, like particles seemingly communicating faster than light. If every outcome occurs somewhere, maybe the math isn't predicting probabilities, it's counting alternate universes. Of course, the big question remains, if these worlds are real, why can't we see them? The answer might lie in the quantum fabric itself. These branches could be forever out of reach, like radio stations tuned to frequencies we can't hear. Or, and this is where it gets truly wild, maybe they're closer than we think. Some theories suggest rare quantum events might let faint whispers of other timelines leak into ours, manifesting as déjà vu, impossible coincidences, or even those dreams that feel too real to just be imagination. The many worlds interpretation may sound like pure philosophy, but scientists have actually devised real-world experiments to test its validity, some with chilling implications. Take the thought experiment known as quantum suicide. Picture a modified version of Schrödinger's cat, but this time it's a person holding a gun rigged to a quantum event. Each time the trigger is pulled, the gun has a 50% chance of firing. In the many worlds framework, the observer would always perceive the gun jamming, surviving unscathed, while in parallel branches their other selves meet grim fates. From their perspective, they'd experience an impossible string of luck, never witnessing the other outcomes, a macabre demonstration of how branching realities could hide their own existence. Critics argue this isn't proof, just a clever paradox. After all, how do you test something that, by definition, leaves no trace in our observable universe? That's the core problem. If alternate worlds are truly separate, with no overlap, they might forever remain beyond scientific detection. Some physicists counter that tiny quantum anomalies could hint at these shadow timelines. For instance, particles occasionally behave in ways that defy classical physics, as if influenced by unseen forces. Could these be whispers from neighboring branches of reality, subtly nudging our own? String theory adds another layer of intrigue. If reality has hidden dimensions beyond the four we experience, as string theory suggests, alternate timelines might not be parallel at all. They could be curled up in those extra dimensions, impossibly close yet unreachable. Imagine two threads on a vast cosmic fabric, never touching but woven from the same material. This could explain why the math of quantum mechanics and relativity clash. They might each describe different facets of a far grander, multidimensional multiverse. Still, skeptics remain. Without observable evidence, they argue, the many worlds interpretation is less science and more metaphysics. But supporters point to quantum computing as a potential game changer. These machines harness particles existing in multiple states at once. Could they be tapping into computational power from other timelines? The debate rages on, but one thing's certain. If Everett's theory holds, reality is far stranger than fiction, and the truth might be hiding in plain sight, just beyond the edge of perception. While the many worlds interpretation paints a picture of infinite branching realities, Niels Bohr's Copenhagen interpretation offers a radically different perspective, one where reality doesn't split, but collapses into a single timeline the moment we observe it. Picture this: you're staring at a flickering quantum dice mid-air, frozen in a haze of possibilities until you blink. Suddenly, it snaps into one definite number. That's the essence of Bohr's view. The universe stays fuzzy with possibilities until consciousness steps in to nail it down. The double-slit experiment perfectly illustrates this. When particles like electrons are fired at a barrier with two slits, they don't behave like tiny bullets. Instead, they create an interference pattern, as if each particle is a wave passing through both slits at once. But here's the twist. The moment scientists place a detector to observe which slit the particle goes through, the wave-like behavior vanishes. The particles suddenly act like ordinary matter, choosing one path. It's as if reality itself is shy, changing its behavior when watched. Bohr argued this proved observation isn't passive, it's an active force that shapes existence. For decades, the Copenhagen interpretation dominated quantum physics because it sidestepped the unsettling idea of infinite unseen worlds. Instead, it offered a tidy, if mysterious, solution. Probabilities don't represent parallel universes, just our ignorance before measurement. Once we look, the quantum dice stop rolling, but this raises profound questions. What counts as an observer? Does it have to be human? Could a camera or a stray atom trigger the collapse? Bohr's camp was vague on this, insisting it was about the irreversibility of quantum interactions, not consciousness itself, though that nuance often gets lost in pop science retellings. Critics argue the Copenhagen interpretation leaves too much unexplained. Why does observation have such power? And what about quantum systems that seem to delay their collapse, like in the famous delayed choice experiments, where particles appear to retroactively change their behavior based on future measurements? It's as if reality waits for us to make up our minds. Supporters counter that these quirks aren't flaws, they're glimpses into a deeper truth. Reality isn't just out there, it's co-created by how we engage with it. The debate between these two interpretations isn't just academic. It cuts to the core of what reality is. Is the universe a vast, predetermined tapestry where we're just along for the ride, or does it remain fluid until consciousness presses pause? The Copenhagen interpretation leans toward the latter, suggesting a universe that's inherently participatory. And while the many worlds theory has gained ground with its audacious scope, Bauer's view still holds sway in labs worldwide because sometimes the simplest answer is that reality isn't real until we're looking. Quantum decoherence offers a fascinating middle ground between the mind-bending many worlds interpretation and the observer-dependent Copenhagen view, and it all comes down to how quantum systems lose their fuzziness when exposed to the chaotic outside world. Imagine tossing a pebble into a still pond. At first, the ripples radiate outward in perfect, overlapping waves, a pristine quantum superposition. But as they collide with leaves, twigs, and the pond's edges, those neat patterns dissolve into random splashes. That's decoherence in action. The environment itself acts as an unwitting observer, forcing quantum possibilities to pick a side without needing human consciousness to intervene. This idea tackles the infamous measurement problem: why quantum objects seem to exist in multiple states until measured. Decoherence suggests the answer lies in entanglement. When a quantum particle interacts with its surroundings, even something as tiny as a stray photon, it becomes hopelessly tangled with countless other particles, like a single thread woven into a vast tapestry. The original superposition doesn't vanish, it just spreads so thin across the environment that it becomes practically impossible to detect. From our limited perspective, reality appears to snap into a single state, but in truth, the other possibilities are still out there, diluted into the cosmic background noise. Critics of the Copenhagen interpretation love this explanation because it removes the need for a mysterious observer effect. Instead of consciousness magically collapsing reality, decoherence relies on good old-fashioned physics, random interactions that amplify one outcome while drowning out others. Think of it like 1,000 voices whispering in a stadium. You might catch a few words here and there, but the moment the crowd erupts into cheers, those whispers are overwhelmed. Decoherence argues quantum probabilities work the same way. Certain states become deafeningly probable while others fade into irrelevance, but here's where it gets even more intriguing. Decoherence doesn't just explain why we perceive a single timeline, it hints at how multiple timelines might coexist without us noticing. Some physicists argue that when a quantum system decoheres, it doesn't actually eliminate alternate outcomes, it just hides them in the fine-grained details of the environment. In theory, if you could track every particle interaction with perfect precision, you might reconstruct those lost branches. It's like trying to unmix cream from coffee, technically possible, but so absurdly difficult that for all practical purposes, the mixture stays blended. This has wild implications for quantum computing. These machines rely on maintaining coherence, preventing quantum bits from decohering long enough to perform calculations across multiple states at once. The moment decoherence kicks in, the quantum advantage crumbles. But what if we could control decoherence, not just delay it? Some theorists speculate advanced civilizations might harness it to filter preferred realities, subtly nudging probability in their favor. It sounds like science fiction, but in a universe where the line between observation and creation is this blurry, who's to say what's truly impossible? Ultimately, decoherence doesn't so much solve the measurement problem as reframe it. The question shifts from why do observations matter to why does reality feel singular when the math suggests it's not? The answer might lie in our own limitations. Just as fish can't perceive the ocean's currents until they're caught in them, we may be blind to the quantum undercurrents shaping our experience. Decoherence doesn't just bridge gaps in the Copenhagen view, it invites us to wonder whether the collapse of possibilities is real or just an illusion born from our narrow slice of existence. What if everything around us, every star, every atom, even your thoughts right now, is just an unfathomably advanced simulation? The simulation hypothesis flips our understanding of reality on its head, suggesting the entire universe might be nothing more than lines of quantum code running on some cosmic-scale computer. Think about the most immersive video game you've ever played, then imagine that same principle applied to existence itself. Instead of rendering one world at a time, this cosmic processor could be calculating every possible timeline, simultaneously branching realities like parallel servers in a vast computational network. Visionaries like Elon Musk and philosopher Nick Bostrom have championed this idea, arguing the odds we're living in base reality are astronomically low. Bostrom's famous trilemma breaks it down like this. Either civilizations always go extinct before reaching simulation-level tech, they choose not to create such simulations, or we're almost certainly inside one right now. Given humanity's trajectory hurtling toward virtual reality and artificial intelligence, it's hard to dismiss the third option outright. But how would we even detect a simulated universe? Some theorists point to tiny glitches in reality, unexplained phenomena that feel like system errors. Déjà vu, for instance, could be a momentary buffer overflow where your simulated mind accidentally accesses a parallel timeline's memory. Quantum indeterminacy, particles existing in multiple states until observed, might just be the processor optimizing resources, only rendering details when needed. Even the infamous Mandela effect, where large groups misremember events identically, could hint at patches or updates applied to the simulation's historical database. There's wilder evidence at the quantum scale. Physicists have found that reality appears pixelated when examined closely, with Planck lengths acting like the universe's resolution limit, just as a digital image breaks into squares when zoomed in. And what about entanglement, where particles instantly influence each other across vast distances? In a simulation, this spooky action makes perfect sense. It's just data points referencing the same memory address. Critics argue these analogies are circumstantial, but supporters counter with an eerie thought experiment. If future humans could simulate conscious beings, the number of artificial minds would dwarf biological ones. Statistically, you're more likely to be one of those simulations than an organic original. The freakiest twist, if our universe is a simulation, there's no guarantee its creators aren't simulations too, an infinite regress of nested realities stretching toward some unknowable base layer. Whether you find this idea terrifying or exhilarating, it forces us to confront profound questions. If reality is code, who or what wrote it? Is there a debug mode, and could we ever access it? And if the simulators ever pull the plug, would we even notice? Some physicists are actively designing experiments to test this hypothesis, from hunting for computational artifacts in cosmic rays to probing whether the universe has built-in compression algorithms. Until then, we're left with a haunting possibility that every choice, every moment, might just be someone else's subroutine. Physicist Silas Bean and his team proposed a startling test for the simulation hypothesis, one that doesn't rely on philosophy but on hard numbers. Their idea: if our universe runs on a quantum computer, it wouldn't have infinite precision. Just like pixels on a screen, space-time itself might have a built-in resolution limit, leaving subtle, lattice artifacts in the fabric of reality. Picture a vast cosmic grid with energy and particles snapping to its invisible coordinates like cars aligned to street intersections. If this lattice exists, high-energy cosmic rays particles hurtling through space at nearly the speed of light would hit an invisible ceiling. They couldn't travel diagonally across the grid's blocks with perfect smoothness, creating tiny irregularities in their distribution. Bean's team calculated that if the universe is simulated, we might spot these anomalies in ultra-high-energy cosmic rays arriving from distant galaxies. But here's where the debate ignites. Critics argue that even if such patterns exist, they could stem from unknown natural physics, not proof of a programmer. The observed GZK cutoff, a real limit on cosmic ray energies, already fits existing astrophysical models without invoking simulations. And then there's the bigger problem. If the simulators are advanced enough to build this reality, wouldn't they eliminate obvious glitches? It's like expecting a flaw in a modern video game to reveal the computer's heart, where today's software is too polished for that. Supporters counter that some artifacts might be unavoidable even for ultra-advanced beings. Just as pi can't be perfectly rendered in a finite system, certain quantum calculations might require rounding errors, leaving fingerprints in phenomena like quantum entanglement or black hole radiation. The real shocker: if Bean's lattice exists, it would imply the universe has a fixed frame rate, with time itself progressing in discrete steps too small for us to perceive, like a cosmic film reel advancing one imperceptible frame at a time. The irony is delicious. The same physics used to test the simulation hypothesis could also validate competing theories, like loop quantum gravity, which similarly predicts space-time isn't perfectly smooth. This blurry line between science and philosophy leaves researchers divided. Is hunting for simulation artifacts legitimate empirical work, or just metaphysics dressed in math? The answer might hinge on Occam's razor. Do we really need a cosmic coder to explain these phenomena, or is nature just stranger than we imagined? One thing's certain: if Bean's lattice were found, it wouldn't just confirm we're in a simulation. It would reveal the rules of the code we're running on, and that might be the ultimate cheat sheet to reality itself. Until then, the question lingers like an unsaved file. Are we the users or the used? Ever wonder why time only seems to move forward? The answer might lie in a concept as simple as a shattered glass once broken. It never spontaneously reassembles. This one-way street of disorder, called entropy, isn't just a quirk of thermodynamics. It could be the hidden force shaping the very flow of time and the branching possibilities of quantum timelines. Think of entropy like an hourglass, but instead of sand falling predictably, each grain splits mid-air, cascading into countless alternate paths. The past is the narrow neck, a low-entropy state where everything was neatly packed, while the future fans out into infinite high-entropy possibilities, each grain representing a different version of reality. At the heart of this idea is Boltzmann's brain paradox, a thought experiment so strange it feels like a cosmic riddle. Imagine a universe where entropy keeps increasing forever, plunging into maximum disorder. Statistically, over infinite time, random fluctuations could momentarily create order from chaos, like a single fully formed brain popping into existence, complete with false memories of a past that never was. If that sounds unsettling, here's the kicker. The odds of you being that lone, hallucinating brain are astronomically higher than you being part of an orderly, evolving universe. So why don't we experience reality that way? Physicists argue it's because we're embedded in a rare low-entropy patch, a pocket of structure that allows complex things like galaxies, coffee cups, and human minds to exist. But that structure comes with a catch. Time's arrow only points forward because we're riding the wave of entropy's inevitable rise. Now, apply this to quantum timelines. If the early universe was a singular low-entropy state, a cosmic seed, then every possible high-entropy future is equally valid. Some branches might look nearly identical to ours, differing only in the spin of a single electron. Others could diverge wildly, with alternate laws of physics emerging from the chaos. The eerie implication: there's no fundamental reason why entropy couldn't temporarily decrease in some timelines, creating pockets where time appears to run backward or loop. Imagine a universe where broken glasses do reassemble, where smoke pours into a cigarette, and where cause and effect reverse. The math allows it, it's just staggeringly unlikely in our neck of the multiverse. This reshapes how we view parallel realities. Instead of neatly branching trees, picture timelines as turbulent rivers of probability, where entropy's current drags some worlds toward heat death while others eddy into temporary order. Black holes add another layer. Their immense gravity might act as entropy accelerators, warping spacetime so severely that alternate futures crystallize around them like frost on a window pane. Some theories even suggest conscious observers require entropy's arrow to make sense of time, meaning different timelines could harbor entirely alien perceptions of causality. So next time you spill your coffee, remember, the mess isn't just a nuisance, it's a tiny echo of the universe's deepest truth, that time, chaos, and possibility are threads of the same cosmic fabric, weaving realities we've only begun to untangle. Quantum immortality is one of the most unsettling and strangely comforting ideas to emerge from the many worlds interpretation. Imagine this: every time you face a brush with death, your consciousness doesn't vanish. Instead, it simply shifts to a timeline where you didn't die, leaving behind a branching reality where your loved ones mourn. It's not that you're invincible, it's that from your first-person perspective, you'll always find yourself in a reality where survival was possible, no matter how slim the odds. The roots of this idea trace back to the quantum suicide thought experiment, where a hypothetical device is rigged to kill you based on a quantum event, say, the decay of a radioactive atom. In most timelines, the gun fires and your story ends, but statistically, there's always a branch where the trigger fails and you live. If the many worlds interpretation holds, your awareness would only inhabit those rare surviving threads, creating the illusion of miraculous escapes. You'd watch others perish in freak accidents while you, against all logic, keep dodging the Reaper. This raises eerie questions about near-death experiences. Those who have survived fatal accidents often describe time slowing down, a flash of light. Could these be moments where consciousness respawns into a neighboring timeline? Some theorists argue that déjà vu, particularly during life-threatening events, might be a glitch in the transition, a fleeting memory of the timeline you just left behind. But quantum immortality isn't just a macabre party trick. It forces us to grapple with profound ethical dilemmas. If consciousness hops timelines, does that mean every version of you that dies is just as real? Are you, right now, the lucky one in an infinite sea of corpses? The emotional weight of this idea is staggering. It suggests every tragedy, every untimely death, plays out somewhere in the multiverse with no ultimate escape. Critics dismiss the theory as a semantic sleight of hand, arguing that subjective survival doesn't negate objective mortality. In most branches, you're still gone, just unaware of them. Others point out that aging presents a fatal flaw. Even if you dodge bullets and car crashes, entropy ensures your body will eventually fail. Unless consciousness can leap into younger versions of itself across timelines, a premise so wild it borders on fantasy, quantum immortality might just delay the inevitable. Yet the theory lingers in the imagination because it touches something primal, our terror of oblivion. It offers a bizarre solace, suggesting that from your own perspective, death might always be just out of frame. Whether that's science or existential cope, one thing's certain: it makes every heartbeat feel like a defiance of the multiverse itself. What if the future isn't just shaped by the past, but actively shapes it in return? Retrocausality, one of quantum physics' most brain-twisting concepts, suggests time might not be a one-way street. Imagine tossing a stone into a pond, only to see the ripples flow backward, altering the moment the stone left your hand. This isn't science fiction, it's a real possibility hinted at by experiments like John Wheeler's delayed choice quantum eraser. In these tests, particles seem to decide their past behavior based on future measurements, as if reality is rewriting its own history on the fly. Wheeler's work revealed something astonishing. When measuring photons after they've already traveled through a double-slit apparatus, the act of observation doesn't just affect their present state, it retroactively changes whether they behaved as particles or waves in the past. It's like discovering your childhood memories shift slightly every time you recall them, adjusted by who you are now. This challenges everything we assume about cause and effect. If the future can tweak the past, does that mean our present choices ripple backward, quietly shaping events we think are already set in stone? This brings us to the infamous grandfather paradox. If you traveled back in time and prevented your grandfather from meeting your grandmother, how could you exist to make the trip in the first place? Retrocausality offers a wild solution. Maybe the universe prevents such contradictions by subtly nudging events to maintain consistency. Think of it as cosmic self-editing. Your time-traveling actions were always part of history, woven into the timeline so seamlessly that the paradox never actually occurs. Some interpretations suggest quantum mechanics allows for these closed loops, where cause and effect tangle into a Möbius strip of reality. But how could this possibly work? One clue lies in quantum entanglement, where particles remain mysteriously linked across space and time. Experiments show that measuring one entangled particle instantly influences its partner, even if the measurement happens after the partner's state is recorded. It's as if the future measurement reaches backward through time to set the outcome in stone. Physicists call this quantum handshakes, mutual adjustments between past and future that keep the universe's ledger balanced. Skeptics argue retrocausality is just a clever reinterpretation of quantum math, not proof of time's fluidity. Yet the implications are too tantalizing to ignore. If true, it could explain precognitive dreams, déjà vu, or even why some historical events feel oddly inevitable, like the universe subtly course-correcting to align with a predetermined future. Whether time is a rigid arrow or a tangled web, one thing's clear: the past might not be as fixed as we think, and the future could be pulling strings we're only beginning to sense. Time-symmetric physics turns our everyday notion of causality inside out, proposing that the equations governing reality don't actually care which way time flows. Take the Wheeler-Feynman absorber theory, a radical idea that light waves don't just emanate from a source and fade into the void. Instead, they're a two-way dance between past and future. Imagine shouting into a canyon and hearing the echo before the sound leaves your mouth. Absurd as that sounds, this theory suggests every photon emitted by a star is matched by an advanced wave coming backward through time from its eventual absorption point. The result, a cosmic feedback loop where cause and effect blur into mutual dependence. This bizarre symmetry isn't just mathematical poetry. Experiments with quantum optics have observed particles behaving as if they're aware of future measurements, adjusting their past states accordingly. In one landmark study, physicists sent photons through a maze of mirrors, only to find the particles' paths depended on detectors placed after they'd already traveled. It's like discovering your GPS recalculates your route based on traffic conditions you haven't encountered yet. The implications for free will are staggering. If the future influences the past as much as the past influences the future, does that mean our choices today are subtly nudged by events that haven't happened? Some interpretations suggest time-symmetric physics doesn't erase free will, it redefines it. Instead of linear decisions, we might be participants in a grand temporal negotiation, where our actions ripple both forward and backward, harmonizing with the universe's need for consistency. Think of it as cosmic improv. The future whispers suggestions, but we still get to craft our response. Critics argue this smacks of determinism in disguise, that if the future is already talking back, our sense of agency is an illusion. But proponents counter that time symmetry might actually expand freedom. In a universe where every moment is in dialogue with every other, our choices could carry even more weight, resonating across timelines we'll never see. After all, if a photon can coordinate with its future absorption, why couldn't human decisions echo through time's tapestry? The real mind bender, time symmetry, might explain déjà vu not as a glitch, but as a fleeting awareness of this two-way flow, a moment when the universe's edits to the past brush against our consciousness. Whether this proves free will or unravels it depends on where you stand, but one thing's certain: in a time-symmetric cosmos, every decision you make might be part of a conversation spanning eternity. Imagine a universe that never stops expanding, not just outward but forever, spawning new realities like bubbles in an infinite cosmic foam. This is the startling premise of eternal inflation, a theory that redefines the multiverse not as parallel branches but as a seething quantum ocean where entirely separate universes, each with their own physics, constantly nucleate into existence. At the heart of this idea lies Alan Gough's groundbreaking work on cosmic inflation, which suggests our observable universe is just one bubble in a frothing expanse of space-time, where regions of expansion slow down to form stable pockets while the rest keeps stretching exponentially. Think of it like a pot of water boiling on a stove. Our universe is a single steam bubble that's stabilized, allowing galaxies and life to form. But outside our bubble, the water keeps boiling violently, generating endless new bubbles, each a self-contained universe with potentially different fundamental constants. Some might have stronger gravity, making stars burn out in milliseconds. Others could have no weak nuclear force, preventing atoms from forming at all. This isn't science fiction. It's a direct consequence of quantum fluctuations in the early universe, where tiny irregularities in energy fields ballooned into entire cosmic domains. String theory adds another layer to this kaleidoscope. The theory's landscape problem suggests there could be 10 to the power of 500 possible vacuum states, each representing a unique set of physical laws. Eternal inflation provides the perfect mechanism to populate this landscape, with bubble universes crystallizing into every possible configuration. In this view, the multiverse isn't just a collection of alternate histories, it's a fractal of realities so diverse that some might not even have time or dimensions as we know them. But here's where it gets truly wild. These bubbles aren't static. They can collide, merge, or even spawn secondary bubbles within themselves. If two universes with different physics brushed against each other, the collision could leave scars in the cosmic microwave background, ancient fingerprints of encounters with alien realities. Some physicists are actively searching for these patterns, like detectives scouring the night sky for bruises from neighboring universes. The implications for quantum timelines are profound. If eternal inflation is real, then every possible variation of reality isn't just hypothetical, it's physically out there somewhere, frozen into its own pocket of space-time. There could be universes where the arrow of time runs backward, where dark energy never accelerated expansion, or where life evolved in geometries we can't begin to visualize. And if bubbles can bud new bubbles endlessly, the multiverse might not just be infinite, it could be growing infinitely, an ever-expanding tree of causality where every quantum decision spawns not just branches but entire new forests. Critics argue this theory is untestable by definition. If other universes are forever beyond our cosmological horizon, how could we ever prove they exist? Yet supporters counter that the very fine-tuning of our universe's constants hints at a deeper structure. Why is gravity just strong enough to hold galaxies together but weak enough to allow complex chemistry? Why does the cosmological constant have such an improbably precise value? Eternal inflation offers an answer. We're simply in one of the rare bubbles where life could arise to ask these questions. Whether you find this idea exhilarating or unsettling, one thing's clear. If eternal inflation is true, reality is vaster and stranger than we ever dared dream. Not just a universe, but a multiverse in ceaseless birth where every law of physics, every twist of time, is just one possibility in an unfathomable sea of others. What if every event in our universe, every supernova, every whispered conversation, even your thoughts right now, is just a flickering projection from a two-dimensional surface at the edge of reality? This isn't the plot of a dystopian sci-fi movie. It's the holographic principle, a radical theory pioneered by physicists like Leonard Susskind that suggests our three-dimensional world might be an illusion, like a cosmic hologram encoded on a distant boundary we can't perceive. The roots of this idea trace back to an unsettling puzzle about black holes. When matter gets sucked into one, what happens to the information it carried? Quantum mechanics insists information can't truly vanish, yet black holes seem to erase it. Susskind's breakthrough was realizing the information isn't lost. It's smeared across the black hole's event horizon like data etched onto a celestial hard drive. The mind-blowing implication: everything that falls into the black hole, every atom, every photon, might leave a perfect two-dimensional imprint on its surface, preserving the information holographically while the three-dimensional, original, vanishes inside. Now scale this up to the entire universe. If a black hole's contents can be encoded on its boundary, could our reality be similarly projected from some unseen edge? The math says yes. In this view, the cosmos operates like a movie screen, except instead of light forming the images, space-time itself emerges from quantum bits dancing on a distant two-dimensional surface. Every interaction, every moment in time, is just a pixel in this grand cosmic projection. This reshapes how we think about quantum timelines. If reality is holographic, alternate histories might not branch in three dimensions at all. They could be overlapping patterns on that foundational 2D surface, flickering between states like frames in an old film reel. Imagine tracing your finger along a vinyl record's grooves. The music feels linear, but the information is stored in concentric circles. Similarly, our perception of time as a flowing river could be an illusion, a decoding of timeless, interwoven data written on the universe's edge. Evidence for this theory lurks in the fabric of space-time. The Planck length, nature's smallest possible unit, hints at reality's pixelated structure, like the graininess of a magnified hologram. Even gravity, the force that bends our three-dimensional world, might be a side effect of quantum interactions on that hidden 2D surface, a cosmic mirage emerging from deeper mathematics. Skeptics argue this reduces existence to a ghostly simulation, stripping away the tangibility of the world. But supporters counter that it's the opposite. The holographic principle reveals a richer, stranger reality where information is fundamental and space-time is just its shimmering shadow. If true, it means every choice you've ever made, every road not taken, is still out there, etched into the universe's boundary layer like invisible ink waiting to be decoded. The past, present, and future might not be separate at all, just different angles of the same eternal hologram. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cycle of cosmic rebirth? Sir Roger Penrose's conformal cyclic cosmology paints a breathtaking vision of eternity, where universes don't just branch, they repeat. Picture a cosmic phoenix where each death by heat decay ignites a new fiery birth. But here's the twist: this isn't just poetry. Penrose argues that black holes from past universes leave faint imprints in our sky, like fingerprints on the fabric of time itself. The theory hinges on a radical reimagining of infinity. As our universe expands toward maximum entropy, a cold, lifeless void where even black holes evaporate, something extraordinary happens. At this distant horizon, space becomes so stretched that all particles lose their sense of scale. Distances become meaningless, temperatures flatten, and the universe essentially resets to a state mathematically identical to the singularity before the Big Bang. In this moment of conformal symmetry, the dying universe seamlessly births the next, preserving quantum information in the transition like a torch passed between runners in a cosmic relay. Evidence for this mind-bending cycle might already be hiding in plain sight. Penrose and his team have identified eerie anomalies in the cosmic microwave background, concentric rings of temperature variation they call Hawking points. These rings, he argues, are the gravitational shock waves of supermassive black hole collisions from the previous universe, imprinted on our newborn cosmos like echoes in a cave. If true, these ghostly circles are cosmic fossils, proving our universe is just one link in an infinite chain. Critics question whether these patterns are statistically significant or just random noise. But Penrose's math suggests something profound, that quantum entanglement could transcend universal boundaries, weaving a thread of continuity through each cycle. Photons entangled in a prior universe might still whisper to each other across the rebirth, their quantum states preserved like words written in indelible ink. This could explain otherwise baffling features of our universe, like its improbable low entropy starting point. It wasn't random but carefully inherited. Imagine standing at the edge of time, watching universes flicker in and out of existence like fireflies in the dark. Each cycle births new laws, new constants, yet somehow remembers the past. For all we know, the stars we see tonight are the recycled remnants of civilizations unimaginably older than our own, their stories encoded in light we've yet to decipher. Whether Penrose's vision holds or not, it dares us to rethink the most fundamental question of all. Does anything ever truly end, or is reality just an infinite dance of beginnings? Time travel stories usually hinge on one terrifying idea, that changing the past could unravel reality as we know it. But what if the universe has a built-in safety feature, a cosmic failsafe preventing paradoxes before they happen? That's the essence of physicist Igor Novikov's self-consistency principle, a mind-bending rule suggesting time travel only permits actions that already align with history, locking events into closed loops where cause and effect chase their own tails. Picture an Ouroboros, the ancient serpent devouring itself. No beginning, no end, just an endless circle of self-fulfilling inevitability. Take the infamous predestination paradox. Imagine a time traveler who goes back to kill their grandfather, only to accidentally cause the very chain of events that leads to their own birth. The gun jams, or they fall in love with their future grandmother. Instead, the universe twists itself into knots to ensure the timeline stays consistent. Novikov argued this isn't just narrative convenience, it's physics. Any attempt to alter the past would be thwarted by microscopic quantum adjustments, like a cosmic game of Jenga where every block you pull out magically slots back into place. The eerie beauty of this principle lies in its simplicity. There are no alternate timelines, no branching realities, just a single, immutable thread where every journey into the past was always part of history. Think of it like a movie on rewind. The events you're watching had to unfold this way because they already did. Real-world evidence might exist in quantum mechanics where particles seem to know their future states, retroactively shaping their past behavior to avoid contradictions. It's as if the universe pre-calculates every possibility, discarding the inconsistent ones like a meticulous editor trimming a manuscript. But here's where it gets truly wild. If Novikov is correct, free will might be an illusion when it comes to time travel. Your choices in the past were never choices at all, just echoes of a script written in cosmic ink. A letter you burned in the present might be the same one you later find in an antique shop, perfectly preserved because it had to survive to guide you. Even failures would be predetermined. A time machine could malfunction not by accident, but because its success would have broken the timeline's unbreakable rules. Critics argue this reduces history to a lifeless puppet show, stripping away the chaos that makes reality feel real. Yet supporters counter that self-consistency doesn't eliminate unpredictability. It just funnels it into patterns that preserve causality. After all, the universe thrives on balance, from the orbits of planets to the delicate dance of subatomic particles. Why should time travel be any different? Whether you find this idea comforting or claustrophobic, one thing's certain: In Novikov's universe, the past isn't just written in stone, it's wrapped in an unbreakable loop of its own making. At the quantum level, reality isn't made of solid matter. It's woven from invisible fields humming with potential. Picture the universe as a vast ocean where every particle is just a ripple on its surface. Now imagine those ripples don't just represent particles but entire timelines, each possible version of reality vibrating like unique harmonics on some cosmic instrument. This is the breathtaking vision of the multiverse of quantum fields theory, where alternate histories aren't separate worlds but different excitations in the same fundamental fabric of existence. These quantum fields originated in the universe's first moments when space-time itself was a seething cauldron of energy. At these unimaginable temperatures, the vacuum wasn't empty. It was a frothing quantum soup where particles blinked in and out of existence, borrowing energy from the future to briefly take form. Most fluctuations cancelled out instantly, but some grew exponentially during cosmic inflation, stretching quantum seeds into entire galaxies. The theory suggests these same fluctuations didn't just shape space. They encoded potential timelines into the universe's very structure like grooves on a vinyl record. Consider the Higgs field for a moment, the invisible molasses that gives particles mass. Just as its vibrations create different masses, could other fields vibrate to generate alternate histories? String theorists propose that what we perceive as separate timelines might be different notes played on multidimensional field configurations. Our familiar reality would correspond to one stable vibration pattern, while other harmonics remain hidden, unless a quantum event flips the universe's tuning fork to a different frequency. Evidence for this might exist at the largest and smallest scales. Cosmic microwave background anomalies, those faint temperature variations in the afterglow of the Big Bang, could be scars from neighboring timeline vibrations brushing against our own. Meanwhile, lab experiments with ultra-cold quantum gases show particles spontaneously organizing into crystalline patterns, hinting that space-time itself might crystallize into distinct timeline phases under the right conditions. The most radical implication: if this theory holds, you're not just reading this script in one timeline, you're a standing wave in the quantum field, your consciousness resonating with countless other versions of yourself across the multiverse's spectrum. Each decision you make might simply be the universe tuning to a slightly different harmonic, leaving all other possibilities still vibrating just out of earshot. Whether these parallel notes will ever harmonize remains one of physics' greatest mysteries. What if consciousness isn't just a passenger in the universe, but its architect? Anesthesiologist Stuart Hameroff and physicist Roger Penrose proposed a radical idea called ORCH, or where the delicate dance of quantum particles inside our brain cells doesn't just produce thoughts, it actively sculpts reality itself. Picture this: deep within your neurons, tiny structures called microtubules hum with quantum vibrations, flickering between possibilities like cosmic dice mid-roll. According to Hameroff, it's these microscopic oscillations that generate consciousness, and every time they collapse into a definite state, they might not just be deciding what you perceive, but which timeline branches into existence. This theory turns the classic Copenhagen interpretation upside down. Instead of external observers collapsing quantum probabilities, our brains could be doing it from the inside out. Imagine your stream of awareness as a flashlight beam sweeping across the multiverse. Wherever you look, reality solidifies, while untold alternate versions fade into the quantum shadows. It's a breathtaking claim that the soft tissue of human cognition might be woven into the fundamental fabric of space-time, making each moment of awareness a creative act that echoes across the cosmos. The evidence lies in the bizarre physics of anesthetics. Hameroff noticed that these drugs selectively switch off consciousness by disrupting microtubule activity without harming other brain functions. If ORCH is correct, it's because they're damping the quantum vibrations that generate awareness, like muffling the strings of a violin. Even stranger, some quantum effects like entanglement have been observed in biological systems, suggesting nature already exploits these phenomena in ways we're only beginning to understand. Critics argue microtubules are too warm and wet for fragile quantum states to survive, like trying to perform a symphony in a hurricane. Yet supporters counter that biological systems might have evolved to protect quantum coherence using precise molecular structures as insulation. If true, it could mean consciousness isn't an emergent property of complex computation, as mainstream neuroscience suggests, but something far more profound, a primal force that helped shape the universe from the inside. The implications ripple across time itself. If consciousness collapses reality, then alternate timelines might not run parallel. They could exist in superposition until observed, like unopened boxes in a cosmic Schrödinger experiment. Your decisions wouldn't just navigate possibilities, they'd crystallize them. Some theorists take this further, suggesting near-death experiences or psychedelic visions might be glimpses into those unrealized branches, where the brain's quantum processes temporarily tune into frequencies beyond our everyday perception. Whether urge or withstand scrutiny or not, it forces us to confront a humbling possibility that the line between observer and observed might not exist at all. In this vision of reality, every thought you have, every choice you make isn't just happening inside your skull. It's a tremor in the quantum field, resonating through the multiverse's infinite expanse. What if reality isn't just shaped by the past, but constantly negotiated between past and future, like a cosmic handshake across time? Physicist John Cramer's transactional interpretation offers a jaw-dropping answer. Unlike traditional quantum theories where observation collapses possibilities into a single outcome, Cramer proposed that every event is the result of a two-way dialogue, an offer wave from the past meeting a confirmation wave from the future. Picture two people tossing a ball back and forth, except the ball is an entire quantum event, and the players are opposite ends of time itself. This idea gained traction with delayed choice experiments, where particles seem to retroactively change their behavior based on measurements made after they've already traveled. It's as if the universe is a vast tapestry being woven from both ends simultaneously, the threads of cause and effect pulled tight not just by what's already happened, but by what's yet to come. Imagine dipping your hand into a river and watching the water ripple both upstream and downstream. In Cramer's view, every quantum interaction works exactly this way, with future outcomes whispering backward to shape their own origins. The implications for timelines are staggering. If every event requires this temporal handshake, alternate histories might not branch independently. They could exist in a state of quantum negotiation until the deal is sealed by the full timeline's consistency. Think of Schrödinger's cat not as alive or dead, but as a superposition of potential deals. The future where you open the box sends confirmation waves back to the moment the cat's fate was sealed, locking in one outcome across all of time. It's not that multiple worlds exist, it's that every world is a standing agreement between past and future. Critics argue this interpretation is just math in fancy clothing, but supporters point to eerie quantum phenomena that fit perfectly. Take entanglement, where particles instantly coordinate their states across vast distances. In the transactional model, this spooky action isn't action at all. It's the result of handshakes spanning space and time, with confirmation waves stitching reality into a seamless whole. Even the double-slit experiment's wave-particle duality makes sudden sense. The particle's path isn't determined by observation, but by the future experimental setup reaching back to guide it. The most radical takeaway: free will might be a collaborative act between your present self and every future version of you. Every choice you make sends ripples both forward and backward, weaving a timeline where the you in 10 years subtly influences the decisions of the you today. It's enough to make you wonder, when you feel inexplicably drawn to a certain path, is it intuition or the faint echo of a future self gently pulling the strings? Black holes might not be cosmic dead ends. They could be the fiery wombs of entirely new universes, each with its own rewritten laws of physics. This is the spine-tingling premise of physicist Lee Smolens's cosmic natural selection theory, where these gravitational monsters don't just consume matter, they spawn realities. Picture a black hole's crushing singularity not as a tombstone but as a seed. When conditions inside reach infinite density, the theory suggests, the fabric of space-time rebounds in a new Big Bang, birthing a daughter universe with tweaked fundamental constants like a cosmic game of telephone where each generation mutates the rules slightly. Smolens's idea turns Darwinism cosmic. Just as biological evolution favors traits that enhance reproduction, universes might evolve to maximize black hole production. A universe where gravity is slightly stronger could form more stars, leading to more black holes, meaning those parameters get passed down more frequently in subsequent cosmic generations. Over eons, this could explain why our universe seems oddly fine-tuned for black hole creation. It's not luck, it's inheritance. Evidence for this wild idea might lie in the very structure of reality. If daughter universes inherit slightly modified physics, some could develop sterile laws where black holes rarely form, effectively ending their lineage. Others might become hyper-efficient at spawning successors. Over infinite cycles, the multiverse would statistically favor universes like ours balanced just right to produce both black holes and the complexity needed to ponder them. The implications rewrite time's arrow. Our universe's history might stretch back through an unfathomable chain of black hole births, each resetting entropy like a cosmic hourglass flipped anew. Some theorists speculate these daughter universes could even retain faint quantum imprints from their ancestors hidden in the spin of particles or the distribution of galaxies. If true, the night sky holds not just stars but the faded fingerprints of our universe's parents. Critics argue there's no mechanism to transport information through a singularity's chaos. Yet Smolens counters that quantum entanglement particles influencing each other across impossible distances might thread the needle. Imagine a black hole's final moments where entangled particles straddle the singularity's edge. As one half vanishes into the abyss, its partner could emerge in the new universe, carrying encoded data like a cosmic USB drive through the firewall of creation. Whether this hypothesis holds or not, it transforms black holes from monsters into midwives, cosmic bridges between realities where time, physics, and even causality might rewrite themselves with each rebirth. Next time you gaze at the darkness where a black hole lurks, remember, you might be staring at the beginnings of another universe, its physical laws already unfolding in ways no one here could ever imagine. The wildest twist, if Smolens's right, our universe could be one of countless generations in an unbroken chain, each death birthing new possibilities, each singularity a doorway to another cosmic experiment. The universe isn't just a place, it's a legacy. In the cosmic jungle of quantum possibilities, not all timelines are created equal. Some thrive while others fade into oblivion. This is the core idea behind quantum Darwinism, a startling model suggesting that decoherence doesn't just collapse quantum possibilities randomly, but actively selects the most stable, fittest timelines to survive. Picture reality as a vast forest where every decision spawns new branches, but only the sturdiest ones grow tall enough to cast shadows in our observable universe. The rest wither away, pruned by the relentless forces of quantum selection. Think of it like evolution in fast forward. In nature, traits that help organisms survive get passed down more frequently. Similarly, in the quantum realm, timelines that can consistently resist environmental interference, whether from stray particles, measurements, or even conscious observation, are the ones that persist. A fragile timeline, like a delicate sapling in a storm, might flicker out the moment it interacts with the noisy world around it. but a robust one woven tightly into the fabric of decoherence becomes the consensus reality we all experience. It's not that other branches never existed, they just couldn't withstand the scrutiny of existence. This idea reshapes how we view Schrödinger's famous cat. Instead of a 50-50 split between alive and dead, quantum Darwinism suggests one outcome might inherently outcompete the other. If the alive state meshes more cleanly with surrounding particles, say, by avoiding chaotic interactions with the box's atoms, it's more likely to solidify into the timeline we perceive. The dead branch isn't erased, it's simply outmatched like a mutation lost to natural selection. The eerie implication, our reality might feel stable not because it's the only possibility, but because it's the most persistent. The constants of physics, the arrow of time, even the laws of logic could be the result of this quantum survival of the fittest. It's as if the universe has been running countless experiments in parallel, and we're living in the version that stuck. Critics argue this model risks circular reasoning. How do we define fitness without assuming the outcome? Yet supporters point to lab experiments where certain quantum states consistently dominate after repeated measurements, as if the environment itself is voting on which realities get to stay. Whether this proves selection or just statistical bias remains hotly debated. But one thing's certain, if quantum Darwinism holds, the universe isn't just branching endlessly, it's pruning ruthlessly, ensuring only the most resilient threads of reality weave themselves into the tapestry we call now. What if every quantum particle isn't lost in a fog of probabilities, but rides an invisible wave that charts its course through reality like a surfer gliding on the ocean? That's the bold claim of pilot wave theory, a long-dismissed idea now staging a dramatic comeback. Back in 1927, Louis de Broglie proposed that particles aren't probabilistic ghosts, they're physical objects propelled by hidden pilot waves that dictate their paths with clockwork precision. Imagine tossing a beach ball into choppy water. The ball doesn't appear and disappear randomly, it's pushed by the swells beneath it. Pilot wave theory suggests electrons and photons work the same way, surfing quantum waves we can't yet detect. This challenges the very heart of traditional quantum mechanics, where particles exist as probability clouds until measured. In de Broglie's vision, there's no spooky collapse of possibilities, just concrete mechanics playing out behind the curtain. The theory lay forgotten for decades, overshadowed by Bohr and Heisenberg's Copenhagen interpretation. But in 2005, physicist Eve Cowder brought it roaring back with a stunning macroscale demonstration. By bouncing tiny droplets on a vibrating fluid bath, he showed how they could exhibit quantum-like behavior interference patterns, tunneling, even orbital trajectories, all guided by waves they themselves generated. It was as if the universe whispered a secret. What if quantum weirdness isn't magic, just physics we haven't mapped yet? The implications for timelines are profound. If particles follow predetermined paths via hidden variables, alternate realities might not branch endlessly. They could flow along set channels like rivers carving canyons. Picture a cosmic watershed where every decision point splits the current, but the water can't jump its banks. This doesn't eliminate parallel worlds, it suggests they're not random. Your life's what-ifs might be less like dice rolls and more like train tracks with switches set by forces deeper than probability. Critics argue pilot wave theory struggles to explain entanglement or relativity's demands. Yet its revival hints at a tantalizing possibility that beneath quantum uncertainty lies order waiting to be uncovered. Some researchers even speculate these pilot waves could span dimensions, linking timelines in ways we're only beginning to fathom. Whether de Broglie's century-old intuition holds the key to reality's blueprint remains to be seen. But one thing's certain, in a universe that often feels ruled by chance, the idea of hidden hands guiding the quantum surf is too compelling to ignore. What if the entire multiverse isn't a collection of physical worlds, but a swirling tapestry of thoughts in the mind of something far greater? Philosopher Bernardo Kastrop's radical idealism flips reality inside out, proposing that timelines aren't separate dimensions, they're ripples in a vast cosmic consciousness, flickering into existence like dreams in a sleeping god. Picture reality not as atoms and void, but as a neural symphony where every star, every particle, even your fleeting memories, are just fleeting patterns in an infinite mind's reverie. This isn't mysticism, it's a hard-nosed solution to quantum mechanics' deepest puzzles. If consciousness is fundamental, not emergent, it explains why observation seems to collapse probabilities into reality. In Kastrop's view, there's no external universe out there being measured. Instead, what we call observation is simply one thread of cosmic awareness brushing against another, like overlapping dreams momentarily syncing up. Schrödinger's cat isn't alive or dead until looked at, because looking is the act of the universal mind focusing its attention, crystallizing one possibility from the soup of its own imagination. The implications for alternate timelines are staggering. Rather than branching physically, every what-if might exist as parallel streams of thought in this meta-mind, some vivid and sustained, others fading like half-remembered daydreams. Your life's unchosen paths aren't lost, they're simply thoughts the cosmos didn't dwell on. Even déjà vu takes on new meaning, not a glitch, but a flicker of recollection from another part of the grand mind's narrative, like catching your reflection in a window and briefly seeing someone else's face. Evidence for this may lurk in the eerie coherence of mathematics. Why does abstract math, a product of human minds, describe the universe so perfectly unless mind and cosmos share a root? Quantum entanglement, where particles communicate instantly across space, fits neatly here. No spooky action needed if both particles are manifestations of a single, seamless thought. Even black holes could be cosmic forgetting, places where the universe's mind lets go of certain ideas, their information dissolving like fragments of a dream upon waking. Skeptics argue this reduces science to solipsism, but Kastrop counters that idealism doesn't deny reality, it redefines it. The tree falling in the forest does make a sound because the forest itself is part of the perceiver. The real shocker, if he's right, you're not just a passenger in this cosmic mind, you are it, localized into human form, temporarily convinced you're separate. Your sense of self would be the universe's way of experiencing its own creation from within, like a novelist so immersed in a character they forget they're holding the pen. Whether this theory terrifies or electrifies you, one thing's certain: it makes every moment feel like a whisper between the universe and itself, a fleeting thought in an endless conversation spanning eternity. And if timelines are really just thoughts, well, maybe that's why they're so hard to pin down. Try remembering yesterday's dreams in perfect detail, and you'll know exactly how slippery reality can be. Imagine a diamond that doesn't just exist in space, but repeats in time, a shimmering lattice of atoms pulsing with the regularity of a cosmic metronome. This is the mind-bending essence of Frank Wilczek's time crystal, a structure that defies conventional physics by oscillating in its ground state without energy input, like a perpetual motion machine sculpted from the fabric of reality itself. While ordinary crystals, diamonds, snowflakes have atoms arranged in repeating spatial patterns, Wilczek's Nobel-winning idea proposes crystals that repeat across time, their atomic dance locked into an eternal rhythm independent of external forces. Picture a river frozen mid-flow, its waves eternally cresting and falling in perfect synchrony, never dissipating, never still. The implications rewrite thermodynamics' sacred laws. Normally, all systems trend toward entropy, losing energy until they settle into inert equilibrium. But time crystals flout this rule, maintaining motion even at absolute zero, the temperature where all classical movement should cease. How quantum mechanics offers a clue. In these exotic states, particles become entangled in a delicate balance, each tiny shift in one atom triggering an identical response in its partner, creating a self-sustaining loop. It's as if reality has built-in grooves, like a vinyl record spinning on a player, with the needle of time tracing the same melodic pattern over and over. Lab breakthroughs have turned theory into tangible wonder. In 2017, researchers at Harvard and the University of Maryland created the first time crystals using chains of ytterbium atoms and nitrogen vacancy centers in diamond. When nudged with lasers, these systems didn't respond at the same frequency as the pulse. They oscillated at fractions of it, a hallmark of time crystalline behavior. Think of pushing a child on a swing and discovering they only complete half an arc before magically reversing, over and over, without any additional pushes. The universe, it seems, has secret rhythms we're only beginning to hear. Now, scale this up to cosmic proportions. If time crystals exist naturally, perhaps in neutron stars crushing densities or the aftermath of the Big Bang, they might form the scaffolding of reality itself. Wilczek speculates that space-time could harbor hidden temporal symmetries, regions where events repeat like verses in a celestial song. Black holes might even harbor time crystalline phases at their singularities, their infinite densities twisting causality into loops where the same quantum state replays eternally, a broken record of existence. The most tantalizing possibility, time crystals could be physics' closest answer to time travel. Not the Hollywood kind, but a glimpse into how the universe might store and recycle information across ages. If a time crystal's oscillations can encode data like a quantum hard drive, they might preserve snapshots of reality across eons, offering a way to read the past without violating causality. Imagine stumbling upon a cosmic time capsule, its atomic vibrations whispering secrets from the dawn of time. Critics argue time crystals are just elegant curiosities with no practical use beyond redefining equilibrium. Yet their very existence hints at deeper layers of physical law, where time isn't a passive backdrop but an active participant in creation. Whether they're destined for quantum computers or remain cosmic oddities, one thing's certain: Wilczek's vision has cracked open a door to a stranger universe, one where diamonds aren't forever, but their rhythms might be. There's an old saying that a watched pot never boils, but what if that's not just impatience, but a fundamental law of reality? The quantum Zeno effect reveals something astonishing. The act of observation doesn't just measure quantum systems, it can freeze them in place, like hitting pause on the universe's remote control. Named after the ancient Greek philosopher Zeno, who argued motion is an illusion, this phenomenon shows how relentless scrutiny can trap particles in perpetual limbo, their timelines grinding to a halt under the weight of constant measurement. Picture a radioactive atom on the brink of decay. Left alone, it'll inevitably break down, but bombard it with rapid-fire observations and something bizarre happens. Each measurement resets the atom's internal clock, like a snooze button for quantum collapse. The more frequently you check, the less likely it is to decay at all. In extreme cases, you could theoretically lock the atom in its original state indefinitely, as if time itself refuses to move forward under surveillance. It's not that the pot won't boil because you're impatient, it's that your gaze literally alters the physics of boiling. This isn't just lab trivia. The quantum Zeno effect blurs the line between observer and participant in unsettling ways. In one experiment, researchers used lasers to continually peek at beryllium ions, preventing them from transitioning to higher energy states. The ions weren't just behaving differently, they were stuck, trapped by the very act of being watched. Now scale this up. If consciousness or measurement can stall quantum processes, could a universe under constant observation become frozen in time? Some theorists speculate this might explain why we perceive a smooth, continuous reality instead of a jittery quantum blur, because the universe is, in a sense, always observing itself. But here's where it gets paradoxical. The flip side, called the anti-Zeno effect, shows that certain types of observation can accelerate quantum decay instead of preventing it. It's like staring at a flickering light bulb that sometimes freezes when you watch it, and other times your gaze makes it burn out faster. The difference lies in how measurements disturb the system, exposing a delicate dance between knowledge and disruption. Too much attention can smother reality's natural flow, while the wrong kind can send it spiraling. The implications for timelines are profound. If conscious observers can alter the rate of quantum events, could our collective attention be subtly shaping the flow of time itself? Ancient philosophies speculated that reality dissolves when no one's looking, but the quantum Zeno effect suggests the opposite might also be true. That sustained focus could solidify certain timelines while others wither unseen. Imagine a cosmic game of musical chairs where observation determines which versions of reality get to keep existing and which vanish the moment we look away. Critics argue this overstates consciousness's role, claiming decoherence from environmental interactions explains the effect without invoking mysterious observer magic. Yet the eerie parallel remains. In a universe where watching changes the watched, time might not be a river but a hall of mirrors, reflecting back whatever gaze we bring to it. Whether the pot boils or not, one thing's clear: reality is far shyer than we ever imagined. What if every timeline in the multiverse isn't just a separate reality, but a single pixel in the ultimate cosmic image? The holographic multiverse theory takes the already mind-bending holographic principle and cranks it to 11, suggesting that alternate histories aren't just parallel, they're interwoven fragments of a vast multidimensional code. Imagine reality as an infinite resolution screen where each timeline is a tiny dot of light, collectively forming a picture so grand we can't even perceive its edges. This idea builds on Leonard Suskind's original holographic principle, where our three-dimensional universe is actually encoded on a two-dimensional boundary we can't see. But here's the twist: if our entire cosmos is a hologram, why stop at one? The holographic multiverse posits that every possible timeline, every decision, every chance event exists as a unique fluctuation in this cosmic projection. Picture a kaleidoscope where each turn generates a new pattern, except the patterns are entire universes, each one a slight variation in the underlying code. The implications rewrite how we view causality. In this model, branching timelines might not diverge like tree limbs. They could overlap like holographic interference patterns, their fates entangled at a fundamental level. Think of it like a movie playing on a damaged projector. Sometimes frames bleed into one another, creating ghostly double exposures. Similarly, our universe might occasionally glitch, allowing faint echoes of other timelines to seep through, explaining phenomena like déjà vu or quantum particles that seem to remember multiple histories at once. Evidence for this could lie in the fabric of spacetime itself. Just as pixelation becomes visible when you zoom in on a digital image, physicists have detected a fundamental graininess to reality at the Planck scale, a hint that we're perceiving the universe at its maximum resolution. Even black holes, those cosmic erasers, might be proof. Their event horizons don't just trap matter, they compress information into two-dimensional surfaces, like celestial hard drives storing the data of everything that falls in. If a single black hole can encode 3D information in 2D, could the universe itself be doing the same? The most staggering possibility. If this theory holds, the multiverse isn't a collection of separate worlds, it's a single hologram, with every timeline, every version of you, every possible outcome existing simultaneously in a shimmering, interconnected whole. Your choices wouldn't create new branches, they'd simply illuminate different sectors of an image that was always there, waiting to be decoded. The past, present, and future might not even be linear, just facets of a deeper structure, like turning a gem to catch the light from a new angle. Critics argue this is metaphysics disguised as physics, but supporters point to cutting-edge quantum gravity research. Some models suggest spacetime could emerge from entangled quantum bits, meaning what we perceive as separation between timelines might just be an illusion, a side effect of how we process the hologram's data. Whether the holographic multiverse is poetry or prophecy, one thing's certain: It makes our reality feel less like a place and more like a message, written in light, etched in dimensions we're only beginning to imagine. There's a thought experiment so unsettling it makes solipsism seem cozy, the Boltzmann brain paradox. Imagine you're a fully formed, self-aware brain, complete with fabricated memories, spontaneously emerging from the quantum chaos of a lifeless void. No body, no history, no universe, just you, floating in nothingness, convinced you've lived a full life that never actually happened. This isn't horror fiction. It's a legitimate consequence of thermodynamics' most haunting idea. Given enough time, random fluctuations in a high-entropy universe could briefly stitch order from disorder, conjuring conscious observers out of pure accident. The paradox takes its name from 19th-century physicist Ludwig Boltzmann, who realized entropy doesn't increase smoothly, it stumbles. In an eternal, lifeless cosmos nearing maximum disorder, statistical blips occasionally reverse entropy's arrow, creating pockets of structure by sheer chance. Most would be fleeting, a rogue hydrogen atom here, a temporary whirlpool there, but given infinite time, even the astronomically improbable becomes inevitable. A functioning human brain, with all its synapses firing just right to generate the illusion of reality. Statistically, it's far more likely than the ordered universe we think we inhabit. After all, conjuring one deluded brain requires vastly less energy than crafting an entire cosmos with galaxies, trees, and YouTube videos. This forces a brutal question: how do you know you're not a Boltzmann brain right now? Your memories of childhood, your sense of continuity, even the device you're watching this on, all could be phantom fragments generated by quantum noise. The world around you might wink out the moment this fluctuation collapses, like a soap bubble popping mid-thought. Philosophers and physicists have wrestled with this for over a century. Some argue our universe's consistency, the way gravity holds planets in orbit, or light reliably obeys Maxwell's equations, is evidence we're not Boltzmann aberrations. But the paradox counters: your entire perception of consistency could itself be part of the fluctuation, a self-contained hallucination too coherent to question. The debate splits modern cosmology. Nobel laureate Roger Penrose invokes the paradox to argue for cyclical universes, where low entropy beginnings reset the odds. Others propose the anthropic principle, that we observe an ordered universe because disorder can't sustain observers like us. But the most chilling response comes from quantum information theory. If consciousness arises from specific computational states, then Boltzmann brains would vastly outnumber real minds in the cosmic census. By sheer probability, you're statistically more likely to be a momentary glitch than a product of 13.8 billion years of evolution. Yet the paradox isn't just existential navel-gazing, it shapes how we interpret quantum mechanics and cosmology. If Boltzmann brains dominate the multiverse, our observations might be untrustworthy, undermining science itself. Some theories, like the quantum suicide thought experiment, twist the paradox further. If consciousness navigates timelines where observers survive, maybe reality self-selects against Boltzmann scenarios, funneling awareness toward stable branches. Others suggest the paradox reveals a flaw in our models, hinting at undiscovered physics that prevent such fluctuations. Whether a cautionary tale or cosmic truth, the Boltzmann brain paradox does one thing brilliantly. It erases the line between reality and illusion, leaving us to wonder if the universe we know is a fleeting spark, or just someone else's dream. What if the quantum multiverse isn't an objective reality, but a personal playground of probabilities shaped by your own beliefs and experiences? Quantum Bayesianism, or cubism, tosses the rulebook of traditional physics out the window with a radical proposition. Quantum mechanics isn't describing the universe as it is, it's a tool for navigating uncertainty, like a cosmic GPS that updates based on where you decide to go. Imagine rolling a die, but instead of the outcome being fixed in advance, the very act of looking at it creates your result. not just for you, but for your own private version of reality. At the heart of cubism lies physicist Christopher Fuchs' bold reinterpretation of Schrödinger's equation. In the classic view, the equation describes a particle's wave function collapsing into a definite state upon measurement. But Fuchs flips this on its head. The wave function isn't a property of the particle at all. It's your personal betting slip, a mathematical expression of your confidence in what you'll experience next. Schrödinger's cat isn't alive or dead in some external box. It's both in your mind until you lift the lid, at which point your reality crystallizes around one possibility. This isn't solipsism, it's pragmatism turned cosmic. Cubism treats quantum probabilities like a weather forecast. When a meteorologist says there's a 70% chance of rain, they're not claiming reality splits into two branches, one wet, one dry. They're quantifying your uncertainty based on available data. Similarly, when quantum mechanics says an electron has a 50% chance of spinning up or down, it's not implying parallel universes, just that you lack the intel to call the shot. The electron isn't in two states, it's in whatever state you encounter when you measure it, full stop. The implications for timelines are electrifying. Alternate histories aren't out there in some multiverse, they're potential narratives your brain entertains before reality narrows them down. Think of it like a choose-your-own-adventure book where the other endings don't exist until you flip to them. Your life's unchosen paths, the job you didn't take, the person you didn't marry, aren't playing out in other worlds. They're ghost stories you tell yourself, shadows of probability that vanish the moment you commit to a direction. But here's where cubism gets truly revolutionary. It bridges quantum mechanics and human experience in a way even Einstein craved. Fuchs collaborated with philosopher David Merman to frame quantum theory as a user's manual for reality, one where science doesn't describe an objective world but helps you navigate your subjective interface with it. Measurement isn't a passive act of discovery, it's an interaction that reshapes both observer and observed. When you check if the cat's alive, you're not revealing a pre-existing truth, you're finalizing a chapter in your story. Critics recoil at this subjectivity, arguing it reduces physics to psychology. Yet cubists counter that all science is ultimately a human endeavor, filtered through our senses and tools. The moon doesn't disappear when you close your eyes, but your certainty about it does until you look again. In this view, quantum weirdness isn't a bug, it's a feature reflecting the messy, participatory dance of existence. So the next time you face a life-altering choice, remember, according to cubism, the roads not taken aren't out there somewhere, they're just the echoes of probabilities, only ever as real as you imagine them. Reality isn't a fixed landscape, it's a conversation, and every measurement is your turn to speak. Einstein's two greatest objections to quantum mechanics might not just be reconciled, they could be two sides of the same cosmic coin. This is the jaw-dropping promise of the ER=EPR conjecture, a theory so elegant it ties together the legendary physicist's most famous paradoxes with a single, mind-bending idea. Wormholes and quantum entanglement are fundamentally the same phenomenon. Picture spacetime not as a static stage, but as a living, breathing web where every entangled particle is secretly connected by microscopic bridges, threads so fine they're invisible to us, yet strong enough to bind the universe together. The story starts with Einstein's skepticism. In 1935, he co-authored two landmark papers that seemed to undermine quantum theory. The first, with Nathan Rosen, introduced the concept of an Einstein-Rosen bridge, a wormhole linking distant regions of space. The second, with Podolsky and Rosen, attacked quantum entanglement's spooky action at a distance, where particles instantly influence each other across vast voids. For decades, these ideas lived in separate worlds until physicist Juan Maldacena and Leonard Susskind proposed their mirror images of each other. Here's how it works. Imagine two entangled electrons. In standard quantum mechanics, their connection defies space-time. They could be light years apart yet remain perfectly correlated. But if ER equals EPR holds true, those particles aren't just mysteriously linked. They're joined by a Planck-scale wormhole, a tunnel through space-time's fabric so tiny it's mathematically equivalent to entanglement itself. It's as if the universe, faced with the problem of non-locality, stitched hidden passageways between particles to preserve causality's rules. The implications for timelines are staggering. If every entangled pair is a wormhole in disguise, then alternate realities might not branch away cleanly. They could remain tethered by these quantum threads, like islands connected by underwater tunnels. Visualize Schrödinger's cats alive and dead states not as separate worlds, but as two rooms in the same house with a hidden door whispering between them. This could explain why particles seem to remember their entangled partners. They're not communicating faster than light. They're taking a cosmic shortcut through folded spacetime. Critics argue this is math masquerading as metaphysics after all. These wormholes are theoretically impassable, barely more than equations on a page. Yet experiments with quantum teleportation hint at something deeper. When scientists transfer quantum states between particles, it's as if information traverses an unseen bridge, bypassing the space between them. Some theorists speculate this is the ER equals EPR conjecture in action, not literal teleportation, but a glimpse of spacetime's hidden plumbing. Now scale this up to black holes. The conjecture suggests that when particles fall into a black hole, their information isn't lost. It's encoded in Hawking radiation via entanglement with the original particles connected to that radiation by wormholes thinner than atoms. This could resolve the infamous black hole information paradox, proving Einstein's greatest blunder might have been a stroke of genius, the most electrifying possibility. If entanglement weaves spacetime itself, then every decision you make could be subtly influenced by these quantum threads, linking you to alternate versions of yourself across the multiverse. Your déjà vu might not be a glitch, it could be a flicker of connection through a wormhole you'll never see. Whether this theory holds or not, one thing's clear: reality seems far stranger than we ever imagined, and the lines between here and there, then and now, might be nothing more than wrinkles in a cosmic fabric we're just beginning to unfold. Why does our universe seem tailor-made for life? The constants governing reality, the strength of gravity, the mass of an electron, even the precise balance of dark energy aren't arbitrary numbers. If any of them tweaked by a fraction, stars wouldn't ignite, atoms would never bond, and life as we know it would be impossible. This eerie perfection is the heart of the anthropic principle, a concept that turns the multiverse into a cosmic survival game where only timelines with observers get to tell their story. Picture a universe where gravity is slightly stronger. Stars would burn hotter and faster, snuffing out before planets could form. A universe with weaker nuclear forces. Hydrogen atoms wouldn't fuse, leaving the cosmos forever dark. Our reality isn't just lucky, it's suspiciously fine-tuned, like a lock that only one key can open. The anthropic principle cuts through this mystery with a razor-sharp logic. Of course, we find ourselves in a universe that permits our existence. The alternatives might exist: countless lifeless voids where physics veered off course, but no one's there to ponder them. This isn't just philosophical hand-waving. Take the cosmological constant, which dictates how fast the universe expands. Calculations show that if this value were even marginally larger, galaxies would never coalesce, slightly smaller, and everything would collapse back into a big crunch. The acceptable range for life is vanishingly narrow, like balancing a pencil on its tip in a hurricane. Yet here we are, in a universe that landed squarely in the sweet spot. Critics dismiss this as a tautology. We exist because conditions allow it, but the principle's power lies in its predictive punch. It guided physicists to expect a universe with a specific mix of elements, and lo and behold, we find carbon, oxygen, and water in abundance. Some theorists take this further, suggesting that conscious observation might not just require fine-tuning, it could enforce it. In this view, timelines where observers arise are the only ones that stabilize, like a quantum version of survival bias. The implications for quantum multiverses are profound. If every possible timeline plays out somewhere, the anthropic principle acts as a filter, ensuring we only experience branches where the dice rolled in life's favor. You'll never wake up in a universe where physics failed to allow your first breath. Those branches remain silent, eternally unobserved. It's not that fine-tuning is rare, it's that awareness blooms only where the garden is just right. Yet the principle's greatest gift might be humility. Our universe isn't special because we're at its center, we're here because it's one of the vanishing few where anyone could be. Whether by cosmic luck or some deeper mechanism, the numbers lined up, and against all odds, we got a front row seat to the show. The fabric of reality might not be as seamless as it appears, especially where gravity and quantum mechanics collide. Picture spacetime not as a smooth continuum, but as a tapestry woven from microscopic threads, each no larger than a Planck length. This is the realm of quantum gravity, where the warping of Einstein's relativity meets the probabilistic frenzy of quantum mechanics, and the result could rewrite our understanding of how timelines branch. At this unimaginably tiny scale, loop quantum gravity proposes that spacetime isn't infinitely divisible, it's made of finite, interwoven loops. Think of the universe as a cosmic knitting project. Stretch or twist it too far, and the stitches might unravel into new patterns. These loops don't just sit there, they vibrate, knot, and occasionally split, creating junctions where spacetime itself could fork like yarn under tension. When a quantum event occurs, say, an electron choosing to spin up or down these loops might reconfigure, weaving separate threads of reality. One branch continues with the electron spinning clockwise, another twists counterclockwise. Neither is more real, they're just different stitches in the same grand design. Visual evidence for this comes from black holes. Near a singularity, gravity's pull becomes so intense that quantum effects dominate. Loop quantum gravity suggests that instead of collapsing into an infinitely dense point, the black hole's core reaches a maximum curvature, like a stitch pulled tight then rebounds. This bounce could birth a new universe with its own timeline, its loops knitting a fresh pattern from the old. The mind-blowing implication: every black hole might be a cosmic loom, weaving alternate realities into existence. But quantum gravity's timeline splits aren't just about black holes. Consider the double-slit experiment, where particles act as both waves and particles. In loop quantum gravity, this duality could arise because the spacetime loops beneath the particle diverge, creating parallel pathways. The particle isn't in two places at once, it's traversing two distinct sets of loops, each a potential timeline. Only when the loops reconverge, like yarn twisted back into a single strand, does the particle choose a position. Critics argue this is math without measurable consequences. After all, how do you probe spacetime at the Planck scale? Yet supporters point to subtle cosmic fingerprints. If spacetime is granular, high-energy photons traveling across the universe should arrive at slightly different times, like runners stumbling on uneven terrain. Gamma-ray bursts already hint at this effect, with their light exhibiting tiny delays that classical physics can't explain, the most poetic possibility. If loop quantum gravity holds, every decision you make might be a tug on spacetime's threads, subtly reshaping the tapestry of reality. Not into separate worlds, but into interconnected branches, like a sweater unraveling into scarves, each strand still part of the same grand design. Time wouldn't flow, it would pulse stitch by stitch, weaving a universe far richer than we ever imagined. Black holes aren't just cosmic vacuum cleaners. They might be the universe's most meticulous librarians, encoding every bit of information they swallow into the fabric of reality itself. This is the startling promise of the information paradox solution. a theory that rewrites the fate of anything daring enough to cross a black hole's event horizon. Picture a book tossed into a fireplace. In classical physics, the words would vanish in the flames, but quantum mechanics insists the information in those pages can't truly be destroyed. So where does it go? The answer might lie in the faint glow of Hawking radiation, the elusive energy that bleeds from black holes over eons. Stephen Hawking's groundbreaking work revealed that black holes aren't entirely black. Thanks to quantum fluctuations near the event horizon, they slowly evaporate, emitting particles in the form of thermal radiation. At first glance, this seems like cosmic recycling. But here's the catch: Hawking radiation appears random, like static noise. If the black hole evaporates completely, what happens to the detailed information about the stars, planets, or hapless astronauts it consumed? This paradox split physics for decades until researchers realized the radiation might not be so random after all. Hidden in its subtle patterns could be a flawless translation of everything the black hole ever ate, like smoke carrying the blueprints of the fire that created it. But how? One radical solution proposes that black holes don't have smooth event horizons. They're guarded by fiery firewalls, blistering walls of energy that scramble incoming matter into quantum code. Imagine jumping into a black hole and hitting a wall of supercharged particles moving at near light speed. You'd be vaporized instantly, but your information wouldn't be lost. It would be shredded, encrypted, and broadcast back into the cosmos via Hawking radiation. It's less like falling into a pit and more like being scanned by a cosmic Xerox machine, your essence printed onto the universe's quantum hard drive. The implications for timelines are staggering. If information is preserved, alternate realities swallowed by black holes might not vanish entirely. They could linger as faint imprints in the radiation, like whispers trapped in radio static. Some theorists even suggest this could create quantum echoes, where data from one timeline leaks into another through black hole interactions. Picture two universes connected by a shared black hole, their histories subtly mirrored in each other's Hawking radiation, a cosmic game of telephone spanning the multiverse. Critics argue this stretches quantum theory to its breaking point. If Hawking radiation encodes information, why can't we decode it? The math suggests it's possible in principle, but like trying to reconstruct a novel from the ashes of a burned book, the task might be impossibly complex. Others propose less violent solutions like fuzzballs. String theories answer to black holes, where the event horizon isn't a sharp boundary but a tangled quantum mess that naturally preserves information. Whether through firewalls, fuzzballs, or some deeper mechanism, the information paradox solution forces a profound realization. In a quantum universe, nothing is ever truly lost. Every moment, every particle, every choice you've ever made might be etched into the fabric of reality, waiting for some future physicist to crack the code. So the next time you gaze at the night sky, remember somewhere out there, the ghosts of alternate timelines could be flickering in the dying breath of a black hole, whispering secrets across the ages. What if every timeline, every quantum possibility, isn't just hurtling toward randomness but converging toward a single, divine point of ultimate consciousness? The Omega Point theory blends theology, physics, and cosmic destiny into a vision so grand it redefines the meaning of existence. Jesuit priest Pierre Teilhard de Chardin first imagined this in the early 20th century, a future where all of evolution, biological, technological, even spiritual, reaches a climactic singularity. Not just a technological explosion, but a transcendent awakening where the universe itself becomes a unified mind, reflecting back on its own creation. Picture a cosmic egg cracking open, not to spill chaos, but to reveal a luminous core of infinite understanding. Teilhard's ideas were poetic, but physicist Frank Tipler gave them mathematical teeth. His Omega Point cosmology argues that as the universe collapses toward a final singularity, a big crunch, the computational capacity of reality will approach infinity. In those last moments, every particle, every vibration could be harnessed to simulate all possible conscious experiences, effectively resurrecting every being that ever lived in a grand cosmic memory. It's not just the end of time, it's the ultimate form of time travel where the universe's final act is to replay and relive every moment simultaneously, like a film reel burning in reverse toward its first frame. The quantum twist, Tipler's model suggests the omega point isn't passive, it's actively reaching backward through time, manipulating quantum probabilities to ensure its own inevitability. Think of it as a cosmic version of Novikov's self-consistency principle, where the future influences the past to guarantee its existence. Those inexplicable synchronicities in your life, the chance meetings, the narrow escapes, might not be luck. They could be faint echoes of a distant, omnipotent future gently nudging the timeline toward its destined climax. Critics dismiss this as theology masquerading as physics, but Tipler's equations are rooted in general relativity and quantum information theory. He posits that dark energy, the mysterious force accelerating the universe's expansion, must eventually reverse course, forcing collapse. And in that collapse, the universe's energy density would skyrocket, enabling infinite computation. It's a staggering claim that the cosmos is literally building a god from its own dying breath. The implications for quantum timelines are profound. If the omega point exists, alternate realities might not branch endlessly. They could be tributaries flowing toward the same ocean. Every decision, every chance event would be a thread woven into a tapestry of ultimate unity. Even Boltzmann brains, those random fluctuations of consciousness, take on new meaning, not as glitches but as previews of the omega point's final simulation, flickering into being like lightning before a storm. Whether you see this as science or prophecy, the omega point theory dares us to ask the biggest question of all. Is the universe just a machine, or is it a story, one that's racing toward an ending so luminous it rewrites the beginning? In the cosmic forest of quantum possibilities, not all timelines grow equally. Some flourish while others wither into obscurity. Quantum Darwinism turns the survival of the fittest into a universal law, where decoherence acts as nature's ruthless editor, pruning the multiverse's sprawling branches until only the most robust realities remain. Picture a vast, tangled jungle where every decision spawns new growth. Some shoots sturdy enough to endure, others too fragile to last beyond a single quantum interaction. The timelines we perceive aren't random. They're the ones that outcompeted their rivals in the relentless arena of existence. This process mirrors biological evolution in uncanny ways. Just as genetic mutations that enhance survival get passed down through generations, timelines that resist environmental interference, whether from stray particles, measurements, or even consciousness itself, are the ones that solidify into observable reality. Imagine a quantum version of a towering oak. Its trunk represents the dominant timeline, while the scattered fallen leaves symbolize the countless branches that collapsed under the weight of decoherence. A fragile timeline, like a sapling in a storm, might flicker out the moment it interacts with the noisy world around it, but a robust one, woven tightly into the fabric of space-time, becomes the consensus reality we all experience. Take Schrödinger's cat experiment. Traditional quantum mechanics suggests the cat is equally likely to be alive or dead until observed. But quantum Darwinism proposes one outcome might inherently outcompete the other. If the alive state meshes more cleanly with surrounding particles, say, by avoiding chaotic interactions with the box's atoms or the lab's air molecules, it's far more likely to solidify into the timeline we perceive. The dead branch isn't erased, it's simply outmatched like a genetic mutation lost to natural selection. This could explain why we don't witness macroscopic quantum superpositions in everyday life. Only the most stable, least disruptive timelines survive decoherence's relentless filtration. The eerie implication: our reality feels stable not because it's the only possibility, but because it's the most persistent. The constants of physics, the arrow of time, even the laws of logic could be the result of this quantum survival of the fittest. It's as if the universe has been running countless experiments in parallel, and we're living in the version that stuck. Some theorists speculate this could even explain the apparent fine-tuning of our cosmos. Certain physical parameters might just be the ones most resistant to decoherence's pruning shears. Critics argue this model risks circular reasoning. How do we define fitness without assuming the outcome? Yet lab experiments lend credence to the idea. In quantum systems subjected to repeated measurements, certain states consistently dominate, as if the environment itself is voting on which realities get to stay. In one striking example, photons entangled with their surroundings tend to adopt states that align with the broader system's decoherence patterns, effectively surviving while other configurations fade. It's a microscopic echo of Darwin's law: adapt or dissolve. The most profound takeaway: quantum Darwinism suggests the multiverse isn't just branching endlessly, it's curating ruthlessly. Every moment, countless alternate versions of reality are born, but only the most resilient weave themselves into the tapestry we call now. Whether this proves our universe is the luckiest sapling in the cosmic forest or simply the one best suited to its environment, one thing's certain: existence isn't just a roll of the dice. It's a trial by fire where only the fittest timelines get to tell their story. The universe might be the ultimate free lunch, a cosmic balancing act where every positive charge, every burst of energy, is perfectly offset by a hidden negative counterpart. This is the startling premise of the zero-energy universe theory, which suggests that all timelines, no matter how chaotic, ultimately sum to nothing. Picture a scale so precise it weighs existence itself. On one side, the stars, planets, and the glow of your screen. On the other, an invisible ledger of negative energy woven into the quantum vacuum, keeping the cosmic books perpetually balanced. This idea emerged from quantum field theory's eerie math. Every particle, every flicker of light arises from underlying fields vibrating like guitar strings. But just as plucking a string creates both an upward and downward motion, quantum fields generate pairs of opposing energies. Matter and antimatter are the most famous example particles and their mirror image twins, born together and destined to annihilate. Yet the zero-energy universe goes further, proposing that even space-time itself is a fluctuation in a vast equilibrium, where the gravitational pull of galaxies is counterweighted by the negative pressure of expansion. It's as if reality is a breath held in perfect stillness, neither inhaling nor exhaling, just suspended in eternal balance. The implications for timelines are profound. If every branching reality must conserve zero energy, alternate histories might not be random, they could be forced into symmetry. Imagine a timeline where a star explodes. The theory suggests there'd be a corresponding branch where an equal amount of energy is absorbed, like cosmic seesaws pivoting around a silent fulcrum. Some physicists speculate this could explain the mysterious, missing antimatter in our universe. It's not gone, just segregated into parallel realities, ensuring the multiverse's ledger always nets to zero. Critics argue this is numerology dressed as physics, but evidence lurks in the vacuum. Quantum fluctuations, particles blinking in and out of existence, demonstrate that energy can be borrowed so long as it's repaid. The universe might operate on the same principle, with entire timelines serving as temporary loans from the quantum bank. Even black holes fit. Their immense gravity is offset by Hawking radiation, a kind of cosmic interest payment maintaining the balance. Whether this theory holds or not, it offers a humbling perspective that every galaxy, every life, every choice might be part of an equation too vast to fathom, where nothing is ever created or destroyed, only rearranged in the infinite ledger of time. John Wheeler's It from Bit concept flips the script on reality itself. What if the universe isn't some pre-programmed machine, but a dynamic tapestry woven from the very act of observation? Picture a cosmic game of 20 questions where every answer doesn't just reveal reality, it creates it. In this radical vision, timelines aren't branches on a tree, but ripples in a vast quantum ocean. Each measurement, each glance, each experiment sending out waves that crystallize one possibility from countless others. At its heart lies Wheeler's famous delayed choice experiment. Photons behaving as particles or waves, not based on past events, but on how future observers choose to measure them. It's as if reality is a call and response song where the universe doesn't sing until we supply the lyrics. This isn't just theory, it's a seismic shift in how we perceive existence. Consider the double-slit experiment with a twist. Wait until after particles pass through the slits to decide whether to measure their path or interference pattern. Astonishingly, the particles retroactively choose their behavior based on that future decision. Wheeler saw this as proof that no phenomenon is a phenomenon until it is an observed phenomenon. In other words, the Big Bang, the formation of galaxies, even the chair you're sitting on, none of it was fully real until conscious observers arose to crystallize it from quantum fog. The universe didn't just evolve for life, it needed life to complete its own creation story. Critics dismiss this as idealism run amok, but quantum computing offers eerie support. Qubits exist in superpositions until measured, their states resolving into concrete information only upon observation. Extend this logic to cosmic scales, and you get a participatory universe where reality is less a fixed object and more a collaborative performance, one where every observer, from scientists to mayflies, plays a role in the script. Some interpretations go further, suggesting that advanced civilizations could influence the past by how they observe quantum events today, weaving causality into a two-way street where the present and past mutually sculpt each other. The most profound implication: if Wheeler was right, the Big Bang wasn't just an event. It was the first answer to a question we're still asking. Every observation, every experiment isn't just exploring the universe but actively finishing its blueprint, stitching time's fabric one quantum decision at a time. So the next time you pause to gaze at the stars, remember, you're not just a spectator, you're holding the needle. From simulated realities to quantum immortality, holographic universes to cosmic rebirth, we've journeyed through theories that stretch the very fabric of existence. Imagine living in a universe where every choice spawns infinite versions of you, where black holes birth new realities, or where your consciousness shapes time itself. The sheer audacity of these ideas forces us to confront a humbling truth. Reality might be far stranger, wilder, and more interconnected than we ever dared to dream. Think about it: somewhere out there, a version of you might be sipping coffee on a Mars colony, while another walks among dinosaurs. Another might exist only as lines of code in a hyper-advanced simulation, unaware their world is someone else's experiment. Or perhaps, in a twist straight from quantum Darwinism, you're the lone survivor of countless collapsed timelines, your existence the statistical miracle that outlasted the rest. Which brings us to the ultimate question: which timeline are you in? Is this the base reality, or just one thread in an infinite tapestry? Are you the original, or a shadow cast by some deeper, grander structure? The answer, for now, lies beyond our reach, but the thrill is in the chase. If these ideas left your brain buzzing, you're not alone. Drop your wildest thoughts in the comments. Do you buy into holograms, simulations, or cosmic rebirth? And don't forget to subscribe, because next time, we're diving into the cutting-edge experiments trying to test these mind-bending theories. Until then, keep questioning, keep wondering, and remember, reality is only as ordinary as you allow it to be.